When we started looking at dynamics from Newton's laws, what we found was that when we wanted to change the state of motion of something, we had to apply a force, a push or a pull. So if I want to change the motion of some object, I have to apply a force to it to make it accelerate. When we have something rotating and we want to change its rotation, in other words, maybe either speed it up or slow it down or whatever, change its direction, the quantity that we have to apply to the object is called the torque. So for linear motion, to change the motion, we had to apply a force. For rotational motion, the quantity is called the torque. And the symbol that we'll use for torque is a lowercase Greek letter tau. So capital tau looks like a T, but a lowercase tau is a little bit different than a lowercase t. It's kind of got a, looks like that. I don't know how to describe that. It looks like that. And then kind of a curvy hat on the top. So that's tau. Some people pronounce it taw. I grew up calling it tau, so that's how I'll pronounce it, tau. What I'd like to do is try and go through a physical explanation as to what the torque depends on. What I wish is that you could do this yourself, but hopefully by watching what happens and maybe doing something similar, you'd be able to figure out exactly how these things are related. What I'm going to do is I'm going to use this meter stick, and I'm going to hold the meter stick in one hand. And what I'm going to do is I'm going to apply some forces to this meter stick, and I'm going to use my hand to try and keep the meter stick stationary. The idea is similar to something we talked about before with forces. If one person applies let me draw a diagram here. If there's an object, if one person applies a force like this, and the object starts to accelerate, what would someone else have to do to keep the object from accelerating, to keep the object stationary? They would have to apply an equal but opposite force. So one way of measuring some applied force is to figure out, well, what would I have to do to it to keep the object from accelerating? Well, that's the idea of what we're going to do here. I'm going to apply some forces to rotate something, the meter stick, to rotate the meter stick in one direction, but then I'm going to figure out what would I have to do to keep that thing from rotating, to keep it stationary. So to apply some forces here, I'm going to hang some masses on the meter stick. So I've got a little holder here, and I'm going to hold it here. Now I'm going to apply a force by hanging a mass on this, and that force will tend to rotate the stick. So here's the mass. I'm going to put this mass on here. That mass is going to tend to rotate the stick, and then I have to do something with my hand to keep the stick from rotating. I have to apply a torque in the opposite direction. Without my hand, the stick would rotate this way, but with my hand, I am applying an opposite torque to keep the stick from rotating. So I apply a force, I have to apply a torque on the object to balance that torque. Now, if I increase the force, what happens? I'm going to increase the mass here, increase the force. Oh, what happens? I have to apply more torque. That's the point I'm trying to get across. The greater the force that I apply here, the more torque it's applying. Consequently, the more torque I have to apply to keep the stick stationary. I haven't proven this, but I hope you'll agree that it seems reasonable that if I double the amount of torque from the weight here, if I double the torque from the weight, I would have to double the torque if I double the force with the weight, that's going to double the torque. I would have to pull backwards twice as much, kind of ignoring the mass of the stick anyways. So what does that mean? That means that the torque is proportional to, and again I'm using the symbol proportional to, the applied force. The greater the force, the greater the torque. Okay? So, one of the things the torque depends on is an applied force. Very good. Now, I'm not going to change the force. all I'm going to do is change where the force is applied. I'm going to put the force way down here next to my hand, and I keep the stick stationary. Okay, well that's not too bad. It's pretty easy. Now I'm going to move the force way out here away from my hand, and it's much more difficult, much harder to keep the stick stationary with the force out here. So what does that mean? Well, the closer the force is to my hand, the less torque that's applied. The farther the weight is, the closer the weight is to my hand, the less torque. The farther the weight is from my hand, the more torque. The closer the force is to my hand, the less torque. The farther the force is from my hand, the more torque. Now, what does my hand have to do with it? My hand is what's measuring the torque. My hand is what is applying the counter torque to keep the stick stationary. So my hand is what is doing it and where I'm measuring it. Let's define my hand as the origin. So I'm going to say that the origin is where my hand is, and the distance from the origin to the force, we'll call that R. So let me draw a picture here. So here's the stick, and here's my hand. Okay, yep, there's my hand, and I'm applying a force. And what we have found so far is that the greater the force, the greater the torque. But now, the greater the distance from the origin, so remember, this is the origin, origin, okay, there's the origin. The farther the force is from the origin, the greater the torque. So the bigger R, the more torque. Again, I haven't proven that it's directly proportional. Maybe it's like R squared or R to the 1.5 power or whatever. But let's accept that it's proportional to R, because it actually is. So the torque is proportional to R. If you double R, you double the amount of applied torque. Okay, very, very good. What else? Well, now I'm going to do something. I'm not going to change R, and I'm not going to change F. What I'm going to do is change the angle between R being the vector from my hand to the point where the force is applied. I'm going to change the angle between R and the applied force, and the force is the force of gravity, which is always straight down. If I hold the stick like this, hopefully you can see it. I'm just holding it here, and the mass is hanging down. R is like this now, and F is like this. If R and F are in the same direction, I don't have to apply any torque. In other words, the way I have to rotate my wrist, I don't have to apply any torque. I can hold it with just the tips of my fingers. If I apply the force like this, so that R is now like this and F is like this, again, I don't have to apply any torque. I could balance it on my hand like this, if you can see that. So I'm not doing anything with my wrist again in this case. But when I hold it this way, such that R and F are perpendicular, now it's very difficult to hold in place. I have to do a lot with my wrist to hold this in place. Well, how can we put all this together? If we have R, now R is the vector that goes from the origin to the point where the force is applied. So R goes from the origin to the point where we're applying the force. When they are in the same direction, in other words, when the angle between them is 0, we get 0 torque. When the angle between them is, what's that, 90 degrees, we get a lot of torque. We get a big torque. When, okay, remember I'm holding it like this, balancing it on my hand, when R is this and F is this, notice F always downwards from the force of gravity. When they are in opposite directions, in other words, when theta is 180 degrees, again, we get 0 torque. Well, what does that look like? 0 when theta is 0, 0 when theta is 180, something bigger, or at least not 0 when theta is 90 degrees. What does that look like? Sine of theta, sine of the angle. Well, it turns out those are the only things that the torque depends on, so we can write this as an equality. The torque equals RF sine theta. There we go. Very, very good. This torque is then the quantity that tends to rotate objects, that tends to make objects rotate, change their rotational properties. First, or next, what are the units of torque? Units of torque will be the units of R. R is a position vector, or just meters, times units of F, newtons, times units of sine theta. Sine of an angle is unitless, so we end up with units of torque equals meters times newtons, or newton meters, which you might think is a joule. And a newton meter we typically do think of as a joule. However, whenever we're talking about torques, rather than confusing them with energies, we'll always make sure to leave the units as newton meters, or some quantity of newton meters, milli-newton meters or something like that, whatever. But some combination of newtons and meters. Don't write these as joules. Leave it as a newton meter. Okay, very good. So we have as our definition of torque, tau equals RF sine theta. This might look like a very complicated thing, but I want you to understand that there is nothing here that you don't use every single day, practically, I would imagine, and that you understand in a subconscious way. Because you use this every time you open a door. Let me explain. Let's imagine we've got a door here. I would actually point you to a real door, but there are people out in the hallway and people in a classroom over there, so I'm just going to have to look at a drawing of a door. And let's imagine we want to push this door open. Maybe this is going to swing away from us. When you come up to a door, maybe you're late for class or you're running to get somewhere and you want to open a door quickly. Do you push on the door hard or do you push on the door softly if you want to open it as fast as possible, assuming you want to open it quickly? Well, obviously, if you want to open the door quickly, you push on it hard. You don't push on it a little bit. Why? Because you know the greater your applied force, the more torque is going to swing the door open. The greater the force, the more the door will swing open quickly. Okay, great. Next, when you come to the door, do you push on the door over here near the hinges? You push on the door over here to open it up? Or do you push on the door over here away from the hinges and push on it this way to make it swing open? Obviously, you push on it over here, where the doorknob is, for example, over here away from the hinges. Because if you push on it near the hinges, you know the door is not going to open very much. But if you push on it over here, away from the hinges, it will open easier and more. Because why? Because the greater R, the distance from the axis of rotation, so to speak, in other words, the distance from the origin that the force is applied, the more torque you get. Well, okay, so that makes sense, yeah. The farther from the axis you push, the more the door will open. Okay, now, what about theta? That's the angle between R and F. R is the vector from the hinges, from the origin, to, let's say, the doorknob. When you come up to the door, how do you push on the door? Do you push on the doorknob toward the hinges? This way? Do you pull on the doorknob away from the hinges? No, you come up and you push on the door perpendicular to the door to make it swing open. That's the way to open the door. You'd push on it this way, not this way or this way. In other words, you push on it so that your force is perpendicular to the R vector. So here's R, here's the force. They're perpendicular to each other. In other words, when theta is 90 degrees. So there's nothing here that you don't know subconsciously, you might say, and you put it to use every time you push open a door. But this is a more quantitative form and will allow us to actually use it in solving problems and things like that. All right, excellent.